Right, so today's lesson 78, Systems of Forces, and it's from page 212 of your textbook. Okay, so a person standing in a lift exerts a force acting vertically downwards on the floor of the lift. Okay, so if you imagine a person in a lift, like so, they're going to exert a force downwards. The lift exerts, The lift exerts a force acting vertically upwards on the person. It's like the normal reaction there. Right, let's get this right. That should be an R. We've got a weight downwards there. As the lift moves up and down, the size of the normal reaction changes, but the force that the person exerts on the lift is always equal and opposite to the force the lift exerts on the person. So R equals W. Newton's third law states that for every action there's an equal and opposite reaction. Key point, Newton's third law states that when an object A exerts a force on an object B exerts an equal and opposite force on object A. For instance, if a red ball hits a yellow ball, the force that the red ball exerts on the yellow ball has equal magnitude to the force that the yellow ball exerts on the red ball. These forces act in opposite directions. Example 1. A man of mass 80 kilograms is in a lift of mass 300 kilograms, which is accelerating upwards at 4.1 meters per second squared. You may assume that G is 9.8 meters per second squared. Okay. Work out the tension in the cable pulling the lift by considering the set of forces acting on the man and the set of forces acting on the lift, and then considering the man and the lift as one object. With Newton's third law, explain why we can consider the man and the lift as one object. Okay, so let's do A1 first of all. So we've got a lift containing a man. Okay. And the man weighs 80 kilograms. So we've got, We've got 80G downwards. Okay. We've got a normal reaction upwards. That's from the floor of the lift acting through the man. And then the acceleration is 4.1 meters per second squared. Moving upwards. So this is just, we're ignoring the mass of 300 kilograms now. We're just thinking about the man in the lift. And what we've got, so the net forces on the man is R minus 80G equals 4.1 times 80. So the net force is mass times acceleration. So we've got a normal reaction minus 80G, that way is positive, that way is negative, equals 4.1, that's the acceleration, times the mass of the man, which is 80. So the normal reaction, 4.1 times 80 plus 80G, which is 1,112 newtons. Okay, so I've done this part here. We've done the set of forces acting on the man. Next thing we need to do is the set of forces acting on the lift. So if we think about the lift now, so I'll draw this again here. So if we think about this lift, and we've got a tension in the cable. I'm going to have to do that without air. There we are. And then we've got the man. We've got the man here. So the downwards acting forces on the lift are the man and the weight of the lift. So you get 1,112 downwards because it's equal and opposite. So because there's a normal reaction of 1,112 upwards in the lift from the man, there's going to be equal and opposite 1,112 newtons downwards from the lift. And then there's also going to be 300 G for the weight of the lift. Okay, and the acceleration is 4.1. So we've got T. What do we need to find out? Work out the tension in the cable. Just quick check there. So T minus 1112 minus 300 times 9.8. There are the minuses. There are the pluses. Is the mass, which is now we've accounted for the mass of the man in the 1112, so it's just the lift now. 300 times 4.1. Okay, so T is 300 times 4.1 plus 300 times 9.8 plus 1,112. And it's 5300. All right, at the bottom there, so newtons to two significant figures. Rub some of this off here. So that's A1. Okay, and then part 2. Considering the man and the lift as one object. Now this is the way that I would have done it to start off with, because it's less complicated. So we've got the man and the lift as one object. It's basically 380 G downwards, tension upwards. We've got the acceleration of 4.1 meters per second squared. Okay, so we have T minus 380 G is mass, 380 times acceleration, which is 4.1. So therefore T, which is what we want, the tension in the cord, 380 times 4.1 plus 380 times 9.8. And T is 5,300 newtons, so two significant figures. If you remember 9.8, two significant figures, so we need two significant figures in the answer. Okay, so I'm sure you can see that that second way is a lot quicker. The first way is quite good for helping you see why you get that funny feeling, whether you're going up and down in the lift. So if you're just thinking about the man and the lift, or the person, it could be a woman as well in the lift, you know, that's the uses that's where it's quite interesting. But generally, if you think about the tension in the cable, then you can treat the man and the lift as one object. So part B, with Newton's third law, explain why we can consider the man and the lift as one object. So what we can say, the forces between the lift and the man so that's the downwards and the upwards, cancel each other out. And that's from Newton's third law, equal and opposite. Okay, so they can be ignored, and they can be ignored. And we can treat them as a single object. Okay. Yeah. Example 2. Oh. So we're on a road. A van of mass 1,250 kilograms, tows a trailer of mass 250 kilograms along a horizontal road. Okay, this one should be on the road actually. Let's just put it like that. Okay, so this one is 1,250. And this one is 250. The driving force from the engine is D. So we've got D newtons going forwards. The van experiences air resistance of 300 newtons and the trailer air resistance of 100 newtons. Okay, if the acceleration of the pair of them is 2.4 meters per second squared, calculate the tension in the connection between the van and the trailer and calculate the driving force from the engine. So the tension acts, well, you can imagine there's a connector between the trailer and the van. So there's the trailer and this is the van. Okay, so the tension pulls the trailer along, but actually pulls the van backwards. Okay, they're equal and opposite. Okay, so the tension at the trailer side is pulling the trailer along, and the tension at the van side is sort of holding it back. I think it's sort of intuitive, makes sense. Okay, there's also the normal reaction and the weight due to gravity, but that's going to make my diagram a bit messy, so I'm going to leave this as it is now. And we've got enough information there to work it out. So I'm only looking at horizontal forces. Okay, so I'm ignoring the gravity. You know, for each one there would be an R and an mg. But that's not going to affect, because the driving force is horizontal and the tension in the connection is also horizontal. So if we start with the trailer, T minus 100, we'll do F equals MA for each one, by the way. So T is, that's positive, T is positive, take away the 100 is mass times 2.4. So T is 250 times 2.4 plus 100, 700 newtons. Okay, then if we think about the van, we've got D minus 300 minus T, which is the 700, the same as in the trailer, is mass times acceleration. So the driving force is 1,250 times 2.4 plus 300 plus 700. When you put all those together, D is 4,000 newtons. Okay, example 3. The two ends of a light, inextensible string are attached to two objects of mass 4 and 5. So it comes up and over and down. The string passes over a smooth fixed pulley. The 9 kilogram mass is initially 0.2 meters above the ground, and the 4 kilogram mass is initially 0.6. So that one's 4, and that one's 9. So up to there, 0.2, up to there, that's another 0.4, 0.6 in total for the 4 kilogram mass. And they are released from rest. Okay, so what we've got here, we've got 4g downwards for the 9g for that one. That's for the weight, for gravity. And you've got a tension upwards for that one, and a tension upwards for that one in the string. So A1, an equation of motion for each mass. So if we start with the 4 kilograms one. Now, they are released from rest. They're going to move this way. They're going to move in the direction of the 9 kilogram one because that one's heavier. So that means this way is positive. So clockwise is positive and anti-clockwise one is negative. So for the 4 kilogram mass, T is going to be at the positive one. Minus 4 times 9.8. G is 9.8. Is equals to mass times acceleration. And then for the 9 kilogram one, 9 times 9.8 minus T, okay, because that's going in the positive direction and that T is acting in the negative direction, is 9 times acceleration. That's part 1. Part 2, use these equations to work out the acceleration of the two masses and the tension in the string. Okay, this is equation 1. Equation 2. Now if we do equation 1 plus equation 2, we get, what we actually get is the T's will cancel out. Can you see that one? We're going to add these together because there's a plus T there and a minus T there. They cancel out. So end up with 9G minus 4G. So we've got 5G on the left hand side. Is 13A on the right hand side. So therefore A is 5G divided by 13 meters per second squared. Okay, and then if we substitute for A in 1, say, we get T minus 4.98 equals 4 times 5G over 13. So T is going to be 20G divided by 13 plus 4 times 9.8. And I'll get my calculator now. Oh no, I've already worked them out. So when you simplify these all together, A, the 5G over 13 is 3.8 meters per second squared. That's from there to two significant figures. And let's have another colour for this one. And then T, which is that one there. T is 54 newtons to both to two significant figures. Okay. Yeah. Okay. That needs colouring in as well. That's the green. So the, yeah. So I've done that one. I've done that. I've done that. Right, B. I think if I remember rightly, you need more space for this. Work out the speed at which the 9 kilogram mass hits the ground. Okay, so for the 9 kilogram mass, it starts at 0 meters per second. It has an acceleration and it's the 3.8 meters per second squared that we've just worked out, but I'm going to use it as 5G over 13 to keep it accurate. And it moves, when it hits the ground, it's moved 0.2 meters. And we need to work out the V. Okay. Oh yeah, no, so I need the, I'll be able to fit this on this page. The next one, part C, I need to go on then. Next page is part C, this page is part B. Right, okay, so we've got V squared is U squared plus 2A. V squared equals U squared plus 2AS. Well, U is 0, so V squared is 0 squared plus 2 times A times S. So it's 10G times 0.2. 10 times 9.8 times 0.2 divided by 13 So V is actually the square root of all that, which is 2g over 13, square root, answer 1.2 metres per second to two significant figures. Okay. And then part C. Work out the greatest height of the 4 kilogram mass above the ground in subsequent motion. You may assume G is 9.8 metres per second squared. Okay, so this 4 kilogram mass, okay, so it starts at 0.6 metres above the ground, and then it moves up another 0.2, as moves 0.2 metres. So this is the distance that the 9 kilogram mass moves downwards. So that because the 9 kilogram mass moves down 0.2 metres, it also moves up another 0.2 because of that. Okay, so that's two things to remember. So it's moved 0.8. But then, once the 9 kilogram mass hits the ground, it's still going to go up a little bit because it's still going to have a speed at that point, at the 0.8 metres mark, and it will just go up a little bit further. Okay, so we've got to think what happens. So it starts at 0.6 metres above the ground, and then it goes to 0.8. That's while the that's the at that point the 9 kilogram hits the ground, and then it goes up a little bit further. We need to see how much further it goes. So at this point here, let's do a double star, sorry. At the double star point, I'm running out of stars. Right, so the speed that the speed down here, this velocity that the 9 kilogram mass is moving at when it hits the ground is the velocity that this one is moving at when it's at 0.8 metres. So we can say U is, and I'll go back to the exact answer, square root 2g over 13. Okay, now when it reaches its maximum height, it will just stop for a second. So velocity, or microsecond velocity, will be 0 metres per second. Now at this point, the acceleration stops being the 5g over 13 that we had on the previous page. It's now acting under gravity only. So it's minus 9.8 metres per second squared. Okay, so we've got u, v and an a, and we need to find the s. So it's v squared equals u squared plus 2as. So naught. Now u squared, if u is the square root of 2g over 13, if we square that, it actually becomes 2g over 13. And then it's plus 2 times acceleration times the distance that we need. Okay, so we can have 2 times 9 point, that, oh, with that as well. 2 times minus 9.8 is 19.6, minus on the right, so it's plus, we add it to the other side, 2g over 13. So therefore our s is 2g over 13, and because we've got to divide by 19.6, we multiply it in with that denominator there. So this is the final little bit that this 4 kilogram moves upwards. 2 times 9.8 divided by 13 divided by 19.6. and it's 0. It's funny that 2 times g is actually there as well. Didn't spot that before when I was thinking about this before. They sort of cancel out, so you could just do it as 1/13, I think. Yeah, but anyway, the calculator tells me it's 0.0769, etc, etc, etc. So the total distance above the ground, 0.6 plus 0.2 plus 0.0769, etc, etc, which is 0.8769, etc, etc. So it's 0.88 metres. So 2 significant figures. Okay, so that's an interesting example. The interesting thing here is to note that when it's moving with the string, the acceleration is 5g/13. But once it stops and it's acting under gravity alone, it changes to -9.8. Okay, one more example. A 2 kilogram mass rests on a rough horizontal table. It's attached to a long, let's put this here, 2 kilogram there. 2 kilogram mass is attached, rests on a rough horizontal table. So that means there's going to be a friction when it starts moving. It's attached to a long string that passes over a smooth pulley at the end of the table. So that means it goes like this. Whoops. And it's tied to a 3 kilogram mass. That one's 3. Held still in the air 1 metre above the ground. So there's the ground. Okay, and this is 1 metre. Okay. The 3 kilogram mass is released. The 2 kilogram mass experiences a constant frictional force of magnitude 10 newtons. You may assume G is 9.8. Okay, so this has got 3G downwards. G is 9.8. So that's mass times acceleration downwards. Acceleration due to gravity. We've got a tension there. We've got a tension there. Okay, I think that's everything. That's the ground. We've got normal reaction there and 2G downwards there as well. Okay, so if we think about the part A, work out the acceleration of the two masses and the tension in the string. So this is while they're connected with the string, the acceleration is not going to be 9.8 downwards. I think that comes in later. Anyway, stop thinking on. Right, acceleration and the tension in the string. So if we look at the 2 kilogram mass, we've got, and we're going to go that way, horizontal. Tension in the string, minus 10, that's the net force there, is mass times acceleration. And if we look at the 3 kilogram mass, let's look at that one vertically. So it's going to move this way. So the 3G is positive there. Minus T is mass times acceleration. Okay, call that equation 1, that one equation 2. Do equation 1 plus equation 2. We will get, again, like we had before, the T's will cancel. So we've got 3 G's, which is 3 times 9.8 minus 10. And that's going to be 5 A's, because we've got 2A plus 3A on the right-hand side there. 3 times 9.8, 29.4 minus 10 5a. So a is 19.4 divided by 5 metres per second squared. That will divide nicely actually. So that's going to be 3.88 metres per second squared, and that's not rounded off. Even though we should round it off, I'm not going to round it off just yet. And then if we substitute for a in say 1, we get t minus 10 is 2 times a, which is 2 times 3.88. So t is 10 plus 16, 17, 7.76, 17.76 newtons. So we have that a is 3.9 metres per second squared. T is 18. Newtons, both to 2 significant figures. And that's part A. Part B. Work out the speed at which the 3 kg mass hits the ground. Okay, so we've got U is 0, A is 3.88, S is 1 metre because it hits the ground, travels for 1 metre, and we need to know V. So then we can say V squared is U squared plus 2 times A times S. So V squared is 0 squared plus 2 times 3.88 times 1. So V squared is 7.76. So therefore V is the square root of 7.76. .78, which is 2.8 metres per second to 2 significant figures. Okay. Part C. Work out how far the 2 kg mass travels before it comes to rest. So the 2 kg. So the 2 kg. Let me just think about this. Work out how far the 2 kg mass travels before it comes to rest. Well, it'll travel 1 metre, so it has to be a big table actually. Oh, I suppose no, it's quite a long table. Anyway, it'll travel 1 metre while the, which is the distance that it takes for the 3 kg to hit the ground. So it travels 1 metre, whilst the 3 kg is travelling towards the floor. Okay, so it's at that 1 metre point what happens. Once it hits the floor, then there's no more tension in the string. So the net force, all it's got then is the friction to slow it down. So it's how far it will travel before the friction slows it down to 0. So the friction, so F minus 10, so this is after the first metre. F equals ma, we've got minus 10 is 2 times the acceleration. We don't know what that acceleration is. So acceleration is minus 10 divided by 2 minus 5 metres per second squared. Okay, so we've got, now when it starts, the start of this particular point after the 1 metre, it starts with this velocity, the square root 7.76, and it slows down to 0. So U is the square root of 7.76. V is 0. A is -5. Bingo, we've got 3 things, so we can work out the fourth. And what is it that we want? Time or how far? S is there. So again, it's going to be v squared equals u squared plus 2as. So 0, because 0 squared is 0. U squared, 7.76, because it's the square root of 7.76 squared, plus 2 times a times s. So we're going to have 10s, if we add that 10s to each side, is 7.76. So s is 0.776 metres. So the total distance is, we've got the 1, so it's going to be 1.776 metres, which is going to be 1.8 metres to 2 significant figures. Now part D, I believe I can fit in this little corner here. Work out the magnitude of the force exerted by the string on the pulley. So we've got a pulley there, we've got a tension there, and a tension there. So the tension, it's going to be a tension pulling this way on a pulley, and the tension pulling downwards on the pulley, if that makes sense. Well, when there was a tension, and the tension was actually, where was it at the top? 17.76, let's use the exact answer. Okay, so if you can think of this as a right angle triangle. So the overall force, what do they call it? Let's call it P for pulley. Call it what we like. P. Oh dear. That one. P. So we've actually got a right angled triangle because it's over the edge of a table. It's horizontal and vertical. So P squared is 17.76 squared plus 17.76 squared. So P is the square root 2 times 17.76 squared. Square root answer, which is 25 newtons to 2 significant figures. Okay, that concludes that one.